Everybody. Welcome to the second talk of the day. So our next speaker is Zander Kelley, and he's going to talk about strong bounds for arithmetic progressions of size 3. So take it away, Zander.
Sure. Yeah, so thanks so much for the invitation to come give the talk. This is about the joint work with Raghu Meka. And okay, so a 3-term arithmetic progression. What that is just a triple of 3 numbers that are like evenly spaced like this. So equivalently, there's some solution to this simple linear equation, x plus y equals 2z. And you know, it's like a trivial 3 progression when x and y and z are the same, but if any 2 of them are different, then all 3 of them are different, and we get a non-trivial 3 progression. So there's a very well-known theorem due to Roth, which says that if you have a set within the integers 1 through n with no other property about it besides that it's dense enough, then actually it's guaranteed to contain a 3 progression. So it's saying, well, like this is sort of some combinatorial structure which is unavoidable in any dense set. And he showed this for some density threshold, which is like 1 over log n. And since then, there's been a bunch of work on the problem, like all proving a theorem of the exact same sort, just trying to improve this quantitatively to get this density threshold down as low as possible, you know, towards the known lower bounds. So yeah, so this is the history of the same problem, where you have some dense set A is at least like delta n inside the integers 1 through n, and you're looking for the existence of a non-trivial 3 progression. And yeah, okay, so here like there's like some minor improvements even between these, so I don't want to say this is everything, but roughly, you know, there was a big leap forward early on that got us to like, you know, this 1 over polylog n. And then you can see that the results after that are getting closer and closer to this. It's like a 1 over log n barrier, I'll call it. I'll talk about more, you know, why that's was a barrier for a while in a second, until, you know, just recently, Bloom and Sisask were able to push past this like 1 over log n barrier. And one like nice reason you might like to do that is it like proves the first non-trivial case of like Erdős's conjecture regarding k progressions in dense enough like infinite sets, where that's quantified using like the sum of their reciprocals. But roughly what you need to do that is for any n to go past this like 1 over log n threshold, and it's very nice. Result by Bloom and Sisask was able to do that. Okay, so then our result, again, of the same exact form qualitatively, the difference is in an improvement in this density threshold. So it just says that if A is any set which is dense enough, then it must have some non-trivial 3 progression, and we get this density which is like this funny looking like quasi-polynomial in some parameter function here. And I would say that to get a feel for it, probably the best thing to do is to compare it to this known lower bound due to Behrend. So Behrend shows that for every n, there actually is some set with that's very, you know, reasonably dense. It's like density delta is 2 to the minus log n to the 1/2. And yet it contains no 3 progressions. Something interesting to note about this is like it's substantially better than like a random set. Maybe in a lot of these cases you would expect that to be the extremal example, but you could think about what kind of density you would need for a random set to have no 3 progressions, and it needs to be like substantially smaller than this. So Behrend's lower bound is like a, you know, much higher than a random example. And then what we're able to do is get density threshold, which is like getting pretty close to it. So it's the first kind of bound of the right shape, I suppose. Okay. Yeah, and then I'd like to shift to just talking about it in a slightly different way, where we're actually going to, show the existence of many solutions to this linear equation x plus y equals 2z with x, y, and z all in A. One thing, convenient thing this lets us do is like forget about the difference between trivial and non-trivial solutions. Like there's always only a smallish number of trivial solutions. So as long as you can just show that there are many solutions to this linear equation, that guarantees the existence of some non-trivial solution. So yeah, another way to, the way I'd prefer to say what we prove is that if you have some set A, it has like entropy deficit D, then we're getting this 2 to the minus D to the 12 times n squared solutions to this equation. Yeah, so it's also sensible to think about the same problem over, some different settings. Like, so we could take any finite abelian group G and ask the same problem. If you have a dense set in G, you get a large number of solutions to this equation with x, y, and z all in the set. And like, I want to say that we're not like just being general for the sake of generality. It's like pretty convenient to, first of all, work in the case of finite abelian groups. That's like more convenient. Another reason is it like really emphasizes the abstractness and of the techniques. Like we're really just using some very basic properties that kind of generalize to all finite abelian groups in a sense. Although certain ones are more convenient than others. So you can see here over like the group, which is like the vector space over a finite field, fq to the n, we get somewhat better parameters, getting like 2 to the minus d to the 9 times this n squared number of solutions. And then a follow-up work due to Bloom and Sisask showed how to like take our method and implement it very nicely within any finite abelian group and get the like roughly the same number of solutions we get in the integer case. This makes sense. Like this group, like when you have the cyclic group mod n is roughly equivalent to this setting up to some like tiny difference in the density parameter, translating back and forth between the two questions. So yeah, one thing I want to say is like for the rest of the talk, I'm mostly going to focus on this setting, like both the very nice case of fq to the n and also like using zn as a proxy for the integers. So, okay. Yeah, okay, so let me now give you my interpretation of like what I would say is like the analytic approach to this problem. And I'm trying to leave as many details unspecified as possible and just say what the like basic template of like this analytic approach is. And so what is the approach? So we are given some dense set A, and what you want to do is find some subset A prime, which has like the right number of solutions to this equation, by which I mean like if A prime was like random, roughly. Okay. And then certainly you want A prime to be as large as possible so that we get the strongest conclusion to the problem we want to solve, that we find many 3 progressions within A. And traditionally what has been tried are subsets A prime of the following form, which is just like the restriction of A to some highly structured set V. So here's some options for V. V could be a subgroup, or here's some more general things you could consider letting V be, like a translate of a Bohr set, or also like a generalized arithmetic progression. So I'll give some tiny example about what a Bohr set is in a second, if you're not familiar with it. But yeah, roughly I want to say that they're reasonable things to call approximate subgroups, at least like in a quantitative sense. Now, yeah, so if you this first option would certainly be the nicest. Like if you could just actually consider restrictions to subgroups, but like maybe you're in a group like Zn where n is a prime and you just have no subgroups. So certainly that's not going to do anything for you. So in that case, that's the reason why in general finite abelian groups, we need to consider some approximate subgroups like Bohr sets, like which are always present regardless of the group. But in this nicer case that I talked about, like fq to the n, we can carry out this plan just thinking about subgroups. Yeah, and so here's just like a picture of it. I'm saying, take our set A, we consider the restriction of A to some reasonably large set B, where this restriction becomes well-behaved. So now like this restriction A prime has like a predictable number of solutions, and we're able to control it for some reason. So yeah, okay, this is a summary of the analytic approach. This is like the kind of control you would like. And here, and for the rest of the talk, epsilon is going to be some small constant that doesn't depend on anything else. We'll have some parameters that depend on the density of A, but epsilon will always just be some small constant that's not depending on anything else. And okay, so this is what we would like to do. This is the analytic approach. And yeah, let me say just a small example of like, what are these approximate subgroups? Like, what do they look like? At least one example. So one example is just like an interval in, say, the integers. And I can tell you like a quantitative justification for why you could say that this is an approximate subgroup. So for generic sets of integers, if you looked at this set of all sums of pairs of elements from S, then the like generic thing to get is the number of results you see is roughly S squared. Okay, but then in contrast here, if you take the sum set of the interval with itself, it's only doubling in size rather than squaring. So like in some quantitative sense, it's fair to say that this set is like approximately closed under addition. And that's the kind of property that we need for these approximate subgroups for the approach to be carried out. Yeah, so here, point of this slide, again, is to summarize everything which I'm saying is like an analytic approach to this problem. A small aside for people that are familiar with it is that I'm just like completely trying to ignore the algebraic approaches, like for the cap set problem, which like complicates the story even more. But okay, so finally I can tell you like the way I wanted to try to organize all these previous results as well as our result. Typically, if you have any instantiation of this analytic approach I just talked about, you can like do it anywhere. You could do it here in fq to the n with subgroups, and then you could also do it, in less nice groups with approximate subgroups. Okay, like it might be more painful, but like you can just try to implement roughly morally the same plan in either case. And yeah, one major thing I wanted to highlight is that a lot of the previous works we're working on something which is kind of like orthogonal even to what we do in our work, which is to try to take this basic approach due to Roth and like implement it in this nastier regime where you have to use approximate subgroups, but with as little overhead as possible. Okay, and with that kind of perspective in mind, it makes sense why like you wouldn't expect to go past like 1 over log n. That's like the dream scenario if you're just using the nicest possible kind of class of nice nice sets V, which are subgroups. Like all these works are not even like attempting to do anything besides get as close to this as possible, like albeit using approximate subgroups. Okay, so with that in mind, yeah, my point is there have been relatively few improvements on just like the basic approach in the analytic setting. So another one was due to Bateman and Katz, and they get this like 1 over log n to the 1 plus c, where c is some small constant in this setting. So they have like a new basic approach, and then like even this one it introduced a bunch more complications, and like to port that over to the general case was a big task, and like especially somehow you need to do it without losing this tiny constant c. So like that makes it even harder. And yeah, Bloom and Sisask were able to do that. Like in contrast, we are able to, so we get this improvement, which is like a big improvement already to the basic approach as implemented in this more basic setting. And we have a lot more room to lose when we need to translate it over. And I'll say certainly in translating it over, we use a lot of technology which was developed in these earlier works that were focused on this problem specifically, and how to translate an argument from using subgroups to approximate subgroups as efficiently as possible. Maybe see if anyone has any questions at this point. It's like a good stopping place for a second. Okay, so let me return to my template that I had for what is the analytic approach, and we need to talk about a detail that needs to be instantiated here. So certainly, to be able to do this, we need some property that we're hoping for A prime to actually have, and what that's going to correspond to is some sort of definition for like a pseudorandomness, which is sufficient for the application we have in mind. Okay, so let me just say, what is the notion of pseudorandomness that we'd like? So here, this is for just an arbitrary set within a finite abelian group. So you could imagine drawing two elements, A and A prime, just uniformly at random, and then you say that this is our condition for the set A being pseudorandom, is that if this random variable A plus A prime is near uniform. So we'll talk a little bit about how exactly I want to quantify that, but yeah, this is like basically capturing how we want to measure whether a set is nice or not, is if adding up two random elements from the set is giving you a random variable over G, which is roughly uniformly distributed. And yeah, so I don't know, you can see the definition, it's only sensible for like dense sets. Certainly, if you had a set of size like less than square root G, then you're never going to get something like this. But yeah, for dense sets, it's a reasonable definition of pseudorandomness. And let's see why it's useful for the application. So here, yeah, I'll just write d of x to be like this PDF of this random variable I just talked about. And we're comparing this density function to the uniform density function, which is just 1 everywhere over G. That's like our normalization. Okay, so and so this density function D can like wiggle up and down, and like maybe this is the best thing that we would hope for, is that D is actually just pointwise close, like plus or minus 1 plus or minus epsilon to the uniform density function. It's a very strong condition, but we'll see at the very least that it's sufficient for the application. So what is this telling you? It's telling you that for any set, C, the number of solutions to this equation, A plus A prime equals C, it's roughly what you'd expect if all three sets were random, up to this, multiplicative 1 plus or minus epsilon constant factor, which is certainly good enough for us. Okay, and then so yeah, in particular, right, you can instantiate this with this set G, which is like the like A dilated by 2, which is like the same size as A, and yeah, and then we're getting the number of solutions is roughly what, like A cubed over G times some constant factor, which is certainly plenty. Okay, so this is like the first attempt. I'll say that that will be a little bit too difficult to actually obtain. So we need to weaken this a little bit. So now I'm allowing D to deviate outside this 1 plus or minus epsilon band rarely. Okay, so what I want is that this set of points where it deviates, the density of that set to be like 2 to the minus p for some parameter p. Okay. And yeah, we can see like what kind of control does this give you for different values of p? Well, okay. Remember our set A, it's like entropy deficit is D, right? The size is 2 to the minus D times G. And the set C is the same size. Okay, so if you set P to be just slightly larger than D, then you know the set C is like double the size of this bad set. So you know, you don't have C just concentrated on the bad set. You're getting plenty of points where the density function is like what you would expect. And then in this case, we get like you know, some constant factor also within the number of solutions we would hope for. So yeah, so yeah, here's this new parameter P. Roughly, you can imagine that we're just always wanting to set P to be close to D for the application, although for the rest of the talk, I'll keep them separate so that we can just see how things depend on the density as well as our choice of this parameter for the pseudorandomness condition. Okay, and then something which like, I hope you just believe me on, this condition that I talked about where it's like this epsilon delta condition where you're within this constant band 1 plus or minus epsilon, except for some small fraction delta, which is like 2 to the minus p points, can be roughly captured by this p norm condition as well. It's like a small loss to translate back and forth between those two ways of thinking about it, but in certain contexts, it's more convenient to think about it in one way or the other. I'd encourage you to use like whichever definition you like, but just remember that it's like roughly equivalent to the other one whenever I'm switching between them. So yeah, so I'm saying again, this is like the p norm distance from D to the uniform density function, and we're wanting that to be like you know, roughly at most epsilon, which is like a constant. And yeah, okay, here's just a tiny bit of notation that I want to use. For the entropy deficit of a set, it's just like, you know, a set is this size 2 to the minus D times the group, then I'm saying that the entropy deficit of A is equal to D. Okay. So here we get to like what you could consider to be the main lemma of the proof. And this is for general groups. And yeah, so it's saying that if you have some dense set of the group, the entropy deficit is at most D, then we have this dichotomy. Either the set A is pseudorandom in the sense that we just discussed, okay, or we get some density increment of A onto some highly structured set V, which is like some approximate subgroup. I haven't talked quite yet about why that's useful, but this is like the bulk of the work of the paper is to show this kind of thing, right? If we're in the case one, we're happy we get the number of solutions that we are hoping for. And then the case two, this helps us in some way, which I'll talk about in just a second. And then, yeah, so the other thing to note is that, right, the entropy deficit of the approximate subgroup, it depends on our original entropy deficit. It blows up by some polynomial factor. Yeah, so I'm actually I'll very quickly give another version of this for finite fields, and then, yeah.
So do you also get density increment if you have too many, say, 3-term arithmetic progressions, for example?
Yes, in fact, that's easier. We'll talk about that in a second. In some sense, that's like a better assumption to make. But also, like that is included in this, like right? So our definition of pseudorandomness does have the upper and lower bound, even though for the application you only need the lower bound. We are getting like this control in both directions.
So the P in the near uniform, would that depend on B? The P, no?
Yeah, so sorry, I can just skip to the this version of it, which, oh, it still doesn't have, okay. At the very end, I'll get a good version of this that has the dependence on everything, but this has a d to the 4 times p to the 4. In this case. Okay. So yeah, in any case, it's polynomial in the two parameters we care about, d and p. It has some dependence on epsilon, but epsilon is like a constant. Yeah, great. Okay, so here is just the same thing, this main lemma visualized, showing you, what's happening in these two cases. So either this PDF, right, of the random variable a plus a prime is near uniform in this way that we talked about, or we have the second case, like I'm drawing it like this, I guess, which is, this is the, over here is the pseudorandom case. This is like the structured case. So in the structured case, we can find some reasonably large set V that's also highly structured, where we get this density increment by like a constant factor that, our function is going above this uniform density function by like some constant factor and okay, on a fairly large set V. So what is our plan for this second case? It's like, in a sense, to zoom in on this structured part. Okay, now, right now, I think that's a fair way of thinking of it. Right now, I'm like conflating the difference between the density function D and A itself. However, it's actually like better to get this kind of thing that I'm drawing here. Like by averaging, that means that there's some translation of V where you get the density increment that you needed. Okay, so let me come back to that. Let me just talk about the density increments more specifically. Yeah, so this is the plan, just to finally instantiate all the parts of this analytic approach that we're going to use. So we have our initial set A0, which we set equal to A. We have our initial nice container set V, which is like the whole space. Okay, and then at each step we see, is A pseudorandom? If it is, we get many 3 progressions, because that's like how the quantification of pseudorandomness was designed to guarantee that. Okay, so otherwise we get some density increment. Okay, so we're passing to some subset, zooming in on some AI plus 1, which is just the restriction of AI to some large nice set VI. So in this case, it's actually a subspace or an affine subspace. And then, okay, so since we get a constant factor density increment at each step, this proves that we cannot be in this second case too many times in a row. Like eventually we're going to have to fall into this first case, just because the density that we started with was like 2 to the minus d, and it's growing by this constant factor. That's showing you that you cannot iterate this more than like d over epsilon times before you must be in the first case instead of the second case. And then that's getting you like this overall quantity d to the 9, which is related to what I quoted at the beginning. Right, we're finding a large subset of A, AT, of entropy deficit d to the 9. And within AT, you're getting like the same number of 3 progressions as you would expect for a random set. Let me just go back to show the main lemma instantiated for the simple case. So this is like, over FQ to the n. Yeah, so certainly I'll point out that like the 3 progression problem doesn't really make sense over F2, but this statement does. Like it's a non-trivial statement, which is interesting, over f2 to the n by itself. So if you like, I would encourage you to just think of q is equal to 2. However, it's also interesting for constant q, or even like q is like poly n. Still a reasonably interesting statement. It's like the theorem holds for all q, but for large enough q compared to the little n, it starts to be not interesting. So yeah, just to go over what is the main lemma that we need to prove. It's saying that you have some dense set A of fq to the n. The entropy deficit is like D. And it's telling you that either the PDF of A plus A prime is near uniform, like we would like, or we get some density increment onto some large affine subspace with codimension, which is like D to the 8. Yeah, okay, so let me just try to highlight. There's two main ideas, I guess, that go into the proof, and here's the first one. We call it spectral positivity. And the first thing that I need to do, it's like a small step that's important for the argument, but it's not like the main point, I think, here, which is the following observation. So we're looking at our density function of the random variable a plus a prime. And wait, did I skip a? Yeah, okay, I did. Okay, sorry. Great. Let me talk about this first. Sorry about that. Yeah, so let me just go over. So hopefully you believe me, like everything that we need to do to solve the problem has been reduced to proving this kind of statement. And then for the rest of the talk, I'm just going to talk about this nice case fq to the n. Hopefully you also have been convinced that like if you can get something there, then you can do something more complicated and get things working over more general groups as well.
What would be if A is the subset of the natural number?
Yeah, so like the theorem that we get does only apply to finite abelian groups, although like you can embed that into some cyclic group without really any loss at all. So the point is that if you had like the integers 1 through n, you can embed into like z3n in such a way that you do not get any new solutions to this equation that were not already present. Okay, so it's like allowed to do that. And then you solve the problem there. And then if you get many solutions there, then that tells you had many solutions in the original case. Okay, but yeah, even if you had like a cyclic group, you may need to do something that's not like a subspace. It's like a Bohr set or a generalized progression, like I talked about earlier. I guess I could say that in our actual paper, we do like, in a sense, it's possible to describe the algorithm, the density increment algorithm that we use without embedding into finite groups. Like we are just taking mostly on a sense, density increments onto generalized arithmetic progressions whose rank is increasing slowly. Okay, like, and that's a sensible statement that you can just do in the integers without, you know, it makes sense and you can do it. And it just happens to be that our analysis still needs to embed things into the group. So that's like a little bit different than like embedding into the group, and then like your algorithm is also talking about the group. So anyway. Okay. Yeah, so now I'm just going to go over what do you need to do to prove this main lemma that hopefully you believe it is the important point and all you need to do to finish the proof. So, so what is the setup? So it's like what you would expect. We have this probability density function of the random variable a plus a prime. Okay, we're assuming we're not in the good case, which is the case where it's near uniform. So in particular, we're assuming that d is somewhat different than the uniform density function, and that this difference is detectable to the p-norm. Okay, and then, I mean, this is just writing down like what we wanted our conclusion to be, but I want you like to reinterpret it slightly. Well, actually, maybe I'll get here and reinterpret it slightly. But what we want to do, just following what we wrote down, is find this density increment of the set A onto some large structured set B. Okay. But actually, we're going to try to do something stronger, which is it's sufficient. But we're looking for like a density increment of the density function d itself. Okay, so like by averaging, because d is like a convex combination of translations of A, if you can do this, then like you get a density increment onto one of the translations of A, which means that a translation of B is a density increment onto A. So that's the reduction there. But yeah, I actually want to talk about this. I have like a specific interest in this a particular point here, which is like maybe not that interesting to too many people. So if it doesn't make sense or you don't care, then just ignore it. But yeah, one thing I want to point out here is that this is like somewhat of a leap of faith of the proof. I don't know like of a good way to justify why you should obviously be trying this. Now, I don't want to say like it's also a leap of faith that everybody else who's like worked on the problem has also taken. So I don't want to like claim any special insight there. But yeah, it's interesting to note that there's like you're seriously making a decision about how to proceed here, like pursuing something which is sufficient but not obviously necessary. However, like I can tell you why it would be nice if it were possible. I can justify that in a sense. Okay, so the reason is that like now look at what we're asked to do. Like our assumption is some assumption about the density function d, and we're now seeking like a conclusion about the density function d. Like our assumption is that d differs from the uniform distribution, and this difference is detectable to the p-norm. I want to say that actually this difference from the uniform distribution is detectable by a large subspace. That's like the way that you can think about the problem now, which is, I don't know, already sort of a bit nicer. A second way you could talk about what you've gained by making this decision is the following. So the theorem that we're after, like the main lemma, it falls under like a general class of results which are called inverse problems, where you make some assumption about the convolution of like a set A with itself, and you seek a conclusion about A. So that's like what makes it an inverse problem, is that you would like to pull back some statement about the convolution and conclude something about A. So like here, just from a like proof mechanical perspective, I think it's interesting that we've already sort of completely suppressed the fact that we're working on like an inverse problem. Like if you think that this should be possible, then like I'm no longer need to worry about A, like I don't need to unpack D anymore. That's like done in this very simple argument I just talked about. But yeah, like once you make this step, you decide to pursue this thing. I don't need to unpack D anymore. I just need to make an assumption regarding D, and like I'm seeking a conclusion regarding D. Okay, so yeah, let me talk about what one of the two main ideas that we had. So this is like a small prerequisite to the first idea. I don't think it's like super essential itself, but well, okay, it's maybe essential. I don't know. It's not the main point. But what I want to do is introduce this other probability density function. It's like instead of taking a plus a prime and looking at that random variable, we're looking at this, somewhat different random variable, which is a minus a prime. And yeah, the first observation is just like that it turns out that the p norm distance from uniform of f is never smaller than d. So we can just like go from d to f. And then try to do the same thing we were hoping to do for f. Like this, for the same reason, it will be just as good. F is also like a convex combination of translates of a. So that's just as useful. But yeah, and this, like, you can prove this basically using like Cauchy-Schwarz in the Fourier domain. Yeah, okay. So that's one prerequisite. And then now we get to like the main point. I would say the main point is that, like, if f looks like this, then that's bad. So let me try to talk about what I mean by that. So f, it's promised by our assumption to deviate from the uniform density function. And that deviation is detectable to the p norm. But for like generic density functions, a large deviation downwards does not imply a large deviation upwards. Now, like, because we're normalizing around 1, like this is centered around 1 and it is a density function, like in the 1 norm, it is true that you, like, the same amount of deviation you have downwards is the amount you have upwards. Okay, so but like as you increase p, that becomes less true. And you can think like there's some bad, like the bad example is you have like a uniform density function over some large set that's like its size like 1 minus 2 to the minus p fraction of your set. So what does that look like? It's like, you have some just tiny increase over the uniform density function, and then it goes like all the way down to 0. And it just turns out that like f just can't look like that. Like that's yeah, that's what that's what the claim is here. This is the main point of the observation, is that as measured by the p norm, the magnitude of total deviation downwards is never more than the magnitude of the total deviation upwards, which is like really important for the whole story, right? Like at the end of the day, we would like to witness a density increment of the function. Okay, that's what we were after. Now, like even more stringently, we need to find a witness which is like a structured set V. But certainly, like disregarding the fact that you would like it to be structured, there needs to be some large set where you have a deviation upwards from the uniform density function. Otherwise, you're like have completely no plan. So yeah, it's very important that this is actually this is true. It's just some fact about spectrally positive density functions. So density functions whose Fourier coefficients are all non-negative, is that they just have to be like sort of bouncy in this way, that they can't look like the thing on the left, they have to look like the thing on the right. And yeah, it's like more generally true for I guess positive semi-definite matrices. Actually, it's not even really necessarily a fact just about functions over abelian groups. Is that we have some sort of positive correlation going on, which guarantees that the amount of deviation downwards is never more than the amount of deviation upwards. Okay, this is like the first main idea, I would say. Yeah, now let me talk about the second main idea. Okay, that's supposed to come after, that's fine. Let me just tell you something which I hope you might believe me about, which is that somehow, right, we're trying to deal with this dichotomy, or trying to prove a dichotomy, like that either you're pseudorandom in the way that we expected, or you're like substantially structured in this way that we need. And like, implicitly, the point is that there's nothing in the middle that's like too bad to be pseudorandom, but not good enough to be structured. So you kind of might imagine that the hard case that needs to be handled is this case where A is like roughly pseudorandom, but it has some like planted structured part that you need to somehow detect. Okay, it's like what's causing all the problems, and you need to find it. So here, I think, it turns out that like thinking of some plan which can address this case is able to roughly solve the whole thing. Just if A is itself a subspace, you take the union of a subspace and then like a random set which is somewhat larger than the subspace. Actually, it could be like a lot larger. Even if the random part is a lot larger, it's very possible for the structured part to be like responsible for the majority of the contribution to this, the norm, the p-norm distance of our density function from 1. And I'm saying, yeah, roughly you need some plan for how do you uncover this like planted subspace in this example. And this is the plan that we use. Is that you take A and consider various shifts of A by some group elements S1 through, I guess we just have 1 and 2 here, but and then you consider their intersection. And then what's the point of this is it's supposed to, in the intersection, like all the random part dust is supposed to die, and then you're left over, you haven't found the entire hidden subspace, but you've found like some reasonable sized subset of it, and that's what you need. Okay, so yeah, that's the main idea, and then I'll say like a little bit more specifically, what are we actually doing? So yeah, again, let's look at this density function, and by this stuff we've already talked about, we can actually assume like that F deviates from the uniform density function in this sense, like that the P norm is at least 1 plus epsilon. You might have to change like P slightly to go from what we just talked about to this, but this is measuring like the fact that F has a substantial amount of deviation upwards from the uniform density function. So under this assumption, what are we actually sifting to find in the general case? Like that's not just this specific example. We're using sifting to find the set B. It's like of the form we talked about. You take multiple copies of A, shift them all, and then consider their intersection. And the size, it's important that the size is large. So it's, if you started with a set D, then the size is roughly 2 to the minus dp times A. And what does it do? It witnesses this deviation upwards from uniform in the following sense, like the convolution of B with itself specifically is what I mean. It witnesses this deviation upwards from uniform. And remember, like, what did we want? We wanted a highly additively structured witness. We wanted a subspace. So we haven't gotten there completely, but like we've gotten a step closer. So previously we had in our hands a witness. The only thing we knew about it was that it's large. Okay, so this is getting like a baby step closer to the goal. So we now have a witness with some additive structure of the deviation upwards from uniform. And yeah, so I can give you a summary of the whole thing here. There's this last step that I didn't talk about too much. Roughly, once you have this witness with some additive structure, mild additive structure, at this point you can use some like well-known tools to bootstrap this into like a witness with strict additive structure. And right, so here we are saying that we got this entropy deficit, which is like P times D. This bootstrapping loses you some additional polynomial factors in both P and D, but it gives you an actual, roughly, like, just to say what happens here, you take, you're able to pass to like higher convolutions of more than just 2 sets. Okay, and then once you take like roughly, D convolutions of sets with, yeah, if you have like an iterated convolution of D sets, then you can use some Fourier analysis to say that that's actually very close to some subspace. So that's how you finish the last part. But here, yeah, I just wanted to highlight these are the two main contributions of the work. Is first this idea to use spectral positivity to take our initial witness, which is like given to us just by the assumption of the lemma. It's like completely unstructured. The only thing we know is that it's somewhat large. It has somewhat small entropy deficit. And it shows you the existence of some witness S, which is like witnessing the deviation upwards specifically. Okay. And then we need to use sifting to go from this fact to a witness which was somewhat smaller. It has entropy deficit PD now, but it has more additive structure. And then you continue this at so as we go down, we're trading entropy deficit for additive structure. But at the end, we find a highly additively structured set, this subspace B, still with a reasonably small entropy deficit.
So the structure of B depends on A.
That's true, although it wasn't important that it did.
What do you mean it's not important? I mean, you said that you don't use anything about the structure of F, but then you define B according to the structure of A, which actually defines the structure of F. So,
I see what you mean. Okay. Okay. That's a fair point. So first, let me answer what I thought you were asking about. Which is like, it's not important in the sense that I would be happy to find any set. Okay, that's all I meant. But yeah, you're saying, is there like an interpretation of the entire thing which you actually don't unwrap F ever? That might not be entirely true. So like in the sense that, yeah, you could, so F, certainly we'd want to assume it's like non-negative. But I think even it's possible to like take the convolution of two functions which are sometimes negative and obtain the convolution is like non-negative everywhere. So I'm saying this is like some obstruction to implementing what we have exactly, because yeah, what do I do mechanically to carry it out is I write down F and like the pth power of F. And then I just expand that into like, what is it? It's not a convolution itself, but it's like a weighted sum of some convolutions of sets that look like this. And yeah, are you saying, can you do it entirely abstractly? That's an interesting question. I've tried, yeah, just to see if you can. And I'm not so sure. I think that like certainly some features are not that important, like the fact that one thing that's fine is if F was the convolution of two density functions, which are not necessarily flat. Like I want to say that's like at least a mild thing you might hope also is fine, and that is fine. That's fine. Yeah, how far you can push it, I'm not so sure. But yeah, if you want to get something completely abstract, I feel like the fact that I just talked about is like some barrier to, or I don't know. I don't know how to do it by the same plan at all. So yeah. Okay. So yeah, I guess I mostly did give my summary of this whole thing. The way that I wanted you to interpret it is maybe like depending on your background, you might appreciate the following analogy that like in a sense it's similar to like rounding, you know, a semi-definite program or something. Like at the beginning, you're given some like dual witness witnessing something, and you would like to say like infer from that the existence of a more structured witness, and you're willing to like trade certain things like you know, the exact number epsilon or maybe like the entropy deficit. So yeah, as we're going down here, we're obtaining a witness which is more structured, losing slightly in the like parameter related to epsilon, and then also losing in the entropy deficit. Oh. But yeah, I think that's a reasonable summary of the whole thing. So, yeah, thanks everyone.
Questions?
So are there like obstacles to potentially improving like the exponent in this bound closer to Behrend stuff, or do you have like?
Yeah, I think that's a really interesting question. I would say the most glaring thing is the following. Even like forgetting like the analysis where we lose various polynomial factors at each step, like the basic plan of taking density increments, it's interesting to consider whether that's like going to sensibly give you the right answer. And it's already like, well, it's strange because in like finite fields, you might think like a typical bad example to check is like a Hamming ball. For whatever reason that ends up being bad, I guess, because we have something, it's like in between being additively structured and being like actually additively structured. I don't know exactly how to justify that, but you can go through the calculations and it looks like, okay, I didn't talk about this, but yeah, so you're familiar with like the cap set problem and the parameters you get there. So you get some better parameters, better than Behrend's bound. So something that I think is interesting is that like even the best conceivable implementation that I can conceive of this basic plan where you took density increments, it seems to like never recover that. If you just take density increments, you're already getting like d squared, just like the plan, like even if you had, you know, no loss anywhere else. But I mean, maybe, yeah. But then the other point is, yes, like it's maybe conceivable that you get d squared, like Behrend's bound, basically. If everything else was like ridiculously tight, you had no loss. Like, you know, when we do sifting, we go from d to pd. You need like d plus p. When you do like Sisask and this bootstrapping stuff, you go from like whatever you have to the fourth power. You'd need like to go from you know, again, you need no loss. Like it's conceivable that you could get d plus p for that as well. Actually, I don't know if it's, I shouldn't say that. I don't know if it's conceivable. Like it seems to, if you think that the whole plan should work and you could roughly analyze it in this way, it seems to imply that like these results could be improved way past anything that I could like imagine how to do. But yeah, I mean, maybe it's possible.
Thanks.
So in the sifting, like we have to pick two decides the set value. At exactly the set S, which is the witness for the having the large.
No, so those are unrelated. So here, like you're saying which elements you pick to shift by, that's what you're asking? Yeah, that's an interesting, but I mean, it's certainly not explicit how we're picking them. And in fact, like you could say that you're picking them randomly, but I think that that's even like a bit misleading itself, because it's like a first moment method kind of argument. So like some quantity we need, like we need certain quantities to be good. We need like this to happen, and we also need this to happen. You can come up with a quantity which balances both of them and then apply the first moment method to that, but it really only shows you the existence. Okay, so I'm like summing over all possible choices, and I look at this quantity, and I can conclude the existence of some choice of S which worked for everything. And like, yeah, something that really hammers home why that it's like not really fair to think about it as random is like the exact same calculation works over like an infinite size group. Like I can sum over all the elements in the whole group and like do this like pigeonhole, do this first moment method type argument and find the existence of some choice. But yeah, I don't know that it's how likely you are to find the shifts that work.
So this thing idea is, it's called dependent random.
Sure, yes.
And follows the combinatorics, and it's a well-used idea in graph theory, and you can interpret this.
Yeah.
It's probably worth pointing out that this is a really powerful close to use.
Sure, yeah, so that's true. I mean, if you want to look at it exactly like that. It takes just a little bit of translating things and thinking of these sets as actually specifying some like, bipartite graphs or something. But then, yeah, I agree that like applying it to those bipartite graphs is like exactly like dependent random choice.
And so one great open problem is if you look at some other equations like x plus 3y equals 2z plus 2w, and you want to see how big of a subset of 1 to n you can have without a solution to that. And for an equation like that, it's thought that the exponent actually should be less than 1. And just wondering if any of these analytic ideas could push right now, or if you think that.
Sorry, you mean the exponent of what?
So if you look at equations in 4 variables, there are some of them where we don't know that the exponent is 1 or not. And
what is the exponent? That's
so you're looking at how large of a subset of 1 to n can you get, and like Cedon sets, it's the largest subset of 1 through n you can get is square root of n roughly. And but for the equation x plus 3y equals 2z plus 2w, you want to
so you're saying
non-trivial solutions of that.
Okay, you're saying it's conjecture that you can get like cap set like parameters for that.
Exactly. Okay. Yeah, but the only thing we know how to do is basically these types of methods.
Yeah, so it's a convolution of more sets, right? Roughly like I'm not sure if you say it was like 4 of them.
Yeah. It's an equation in 4 variables.
Okay.
Instead of 3 variables, it's a 1 linear equation.
Yeah, I mean, I think it's sensible that that should help substantially. Like that, the question that I have been thinking about, which is, it seems very related, I guess, is like just, well, I was going to say like polynomial Freeman-Russo, but maybe more accurate to say like the specific approach where you go through like the Bokoli-above problem and yeah, okay, so the problem is to try to find like a large subspace within 4A, right? And you're somehow it needs to come into your argument that like you're using 4A instead of like 2A. I actually have some vague-ish ideas about how to actually make use of that, but I don't know. Yeah, I don't know if they're too related to what I talk. I guess they're somewhat related, but I'd be happy to talk to you about that. Sure.
You seem to be capable of saying anything about circles. So we want to bound subsets of 1 through n with whose different set of being square.
I would think no. I don't think this is the right. Like I think this is an interesting problem, although like that's kind of a problem in a different sort of about a different kind of pseudorandomness than is the essential one here. Like somehow there you're really trying to understand like what is the intrinsic pseudorandomness of like the set of squares in an additive sense. And like here we're more trying to say like what well using pseudorandomness as a tool, but like saying for arbitrary dense sets, we're trying to understand what's the like most pseudorandom large part of it you can zoom in on. So they're a little bit different in spirit. I mean, maybe they could ultimately be kind of mixed, but I haven't seen anything like that happen, I think.
Okay, so let's take any further questions offline, and let's say thanks, Zander, again. We'll return after lunch at 2.